Hello everyone, my name is Seong-Woong Kim. I'm from Inha University. Today, I'm going to present our paper, Generalized Machine Learning with Inha-based data. This is a joint work with Dong-Han Choi, so let's get started. Background as several machine learning is equal to probing neural network. The goal of machine learning is to learn about to acquire new knowledge by training only a few samples of the model, which is a full-time model. If you look at the bottom, as you can see, this is training stage in machine learning. We can start with training samples from base classes, and then train few samples from those classes. And we aim to classify only those classes in one stage. Not only just normal machine learning, there's another power setting called generalized machine learning, where we not only aim to learn about novel classes, but also we have to preserve the existing knowledge for existing classes that are usually called base classes. In generalized machine learning, as similar to the just normal machine learning, we start training with abundant samples from base classes. But when we really train few samples from novel classes, we also use several samples from base classes together. And in first stage, we aim to classify both base classes and novel classes. So both existing work studying when we train novel classes, at the same time, we train the samples of base classes as well. However, there can be some scenario where the base data set cannot be available because of some privacy or ethical issue. Based on this motivation, in this paper, we propose a new generalized machine learning setting, what we call zero-based GFSL. In zero-based GFSL, our goal is still the same as generalized machine learning, which means we have to maintain some performance with base classes and novel classes. In addition, we do the same without any sample of base classes. As you can see, this is a very extreme yet practical version of machine learning. At the first stage, our goal is still the same as GFSL, which means we have to make inference purpose novel classes and base classes. But the different part is, during the training time, while we train the novel classes, we cannot use any base samples, because we assume that our problem setting, there is no available base samples. Actually, in the current literature of GFSL, most existing works focus on transfer learning approaches, which means we fine-tune a pre-trained model with only novel samples, but we observe that these transfer learning approaches lead to the model highly biased toward novel classes. Not only in zero-based GFSL, but also in the existing GFSL setting as well. One matter is actually the decision boundaries. I'm going to explain in details. So, the first stage of transfer learning is pre-training a model for classifier base classes. After the pre-train stage, the feature extractor and base classifier weights are prepared. In the figure on the right side, this result is actually obtained by our own experiment result, which shows that there are some feature vectors in the feature space. In pre-train stage, you can see the well-formed decision boundaries for base classes. But when we fine-tune the model, the decision boundary can change. When we just fine-tune the pre-trained models, we observe the fact that the decision boundary can be highly biased toward novel classes. In the figure, red triangles are the novel classes. You can see that color region taking some portion away from the blue color region used to be the region for the star-based classes. But in our solution, which is actually desired, as you can see, now red triangles and star class areas were separated. We obtain well-balanced decision boundary for both base classes and novel classes. Normalization, which controls the statistics of the weight distribution of novel classifier and base classifier. As summary of our final result, you can see for all the scenario, 1 shot, 5 shot, and 10 shot, in our normalization method, we can achieve almost close to upper bound accuracy and you can see how large the gap between previous work and our work from this figure. So what is wrong with fine-tuning? We first analyze how hard zero-based GFS problem is solved. As I mentioned before, usually transfer learning is widely used in most of GFSL methods. When we apply transfer learning approach to zero-based GFSL, we also follow the same strategy the previous work. We fine-tune only the joint classifier generated by theta with double data set. Even though we freeze the feature extractor, as you can see, the previous experiment result, the accuracy of base classes really bad. We focus on the fact that the feature vector can be changed. Now let's look in the detail. So this boundary can be formed where these two terms are same. Theta times f(x) is usually the final logic that determines the distant boundary. Fx is the feature vector, as I say, still the same because we freeze the feature extractor, but the classifier corresponds to the base classes different to those of double classes. The distant boundary between base classes and double classes will be constructed where these two values are the same. So we analyze how the weight values are distributed. Our first observation is that the variance of weight of base classifier is greater than those of double classes. Because in neural network, given that this assumption, mean of weight is almost close to zero, even after we train the model. Given this assumption, we can have this equation, which means the standard deviation is proportional to norm of weight. In part figure, as you can see, the width of the distribution, which means the variance, base classifier is larger than the double classifier. Importantly, which is somewhat obviously for base classes, we have a lot of samples, which means we can achieve some high level of diversity. But for double classes, we have only few samples, the distribution can be a bit bell-shaped. This is actually well studied by the extinct work as well. Because imbalance between norm of base classes and double classes are well known. So extinct work have attempted to equalize the norm of base classes and double classes. We find that this approach even can make the model more biased to double classes. While the classifier will be highly biased toward double classes, even though the norm of base classes are larger than double classes, which means the variance of base classes is larger than the double classes. We usually find in this work is mean safety phenomena, which means, as you can see, even though the variance of double classes is smaller than the variance of base classes, the distribution entirely shifts in the right direction from the distribution of base classes, which means double classes has more positive values. This mean shifting phenomena, we find that this actually critical region for double bias classifier. So why this mean shifting phenomena happens? Let's see how the gradient is actually computed. When you get propagate from the output, you can see that the gradient with respect to the loss can divide in these two terms. The first term indicates the local gradient, which is already positive because of the Lelu function. But in the second term, is actually the term that can make the negative value because it has an expression y minus kx. The gradient is positive only if y equal to 1, which means the data for the correspond to the class, and it is negative value for all the other class probability. So, as an example, and it's negative value for the other class probability. As an example, cat and bird are double class in these examples. If the cat data is the probability obtained for a double classifier, the gradient can be occur like this is positive gradient, because y is supposed to be 1. We have to increase 0.3, but the bird class we have to increase to 0.3. In the context of double classifier, this will happen. But you think of the joint classifier consists of base classifier and double classifier, because there are many base classes, and there will be at least some portion of the output probability. Let's say some base classes can have 0.05, 0.04, or 0.06. They will all negative gradient. This also positive gradient increases from 0 to 3 to 0 to 4.5, for another bird class 0 to 3 to 0 to 5. If you think only the double classes, the negative gradient is decreased. The total distribution of the double classes will be positive shift from the 0 point. In order to solve this phenomena, we present a new simple but effective normalization method, what we call mean variance classifier normalization, MVCN for short. Our normalization will be processing these two steps. First is online mean centering, next offline variance balancing. Online mean centering performed in online manner in only noble classifier, where our goal is to make the mean of the noble classifier to be close to 0. And then the variance is also imbalance between noble and base classes. We also try to equalize the variance, but this will be done only one purpose for offline manner after all the training done. So these two normalization approaches, our goal is to match the distribution of base classes and noble classes almost the same. Now let's see our experimental results. We use following data set, include ImageNet variant and attribute data set CUV and NWA, which includes semantic input attribute. And also we use following architecture of column tree. These are the compare method. We choose 3 branches of the work. First is architecture-based method and balance fine-tuning, finally and semantic information. As shown in the table, our proposed method, the MVCN, achieves state-of-the-art accuracy we compare with existing GFSL method. Especially, our method performed error 5 and 10 sharp without using any base dataset. This is because mean shifting phenomena gets stronger as we fine-tune model more noble classes, and we achieve the best result using tiered ImageNet similar to mini ImageNet. Also, we are able to observe the same trends in the dataset of generalized learning, which are CUV and NWA. Also, as shown in this slide, you can see that MVCN actually solves mean shifting phenomena achieve a balance between base and noble classes. As a conclusion, in this work, we present the first study on zero-based GFSL, where we do the same as GFSL but using any dataset. Base dataset. First, in GFSL, not only variance, also mean of weight matter to the performance. Second, mean shifting phenomena and variance of the variance can be addressed by online mean centering with offline balancing. Finally, our normalization, what we call MVCN, even enable a simple transfer learning schema to fit of all the other approaches without the base dataset. Thank you for my presentation, and I'm happy to answer questions. Thank you.
Questions?